Here is the next example in the root locus method. The given question, a unity feedback control system has an open loop transfer function g of s is given. He's asking about to sketch the root locus. So basically you have g of s. This is an open loop system. That's a unity feedback system. So that's a unity feedback. If you want, you can put 1 there. It doesn't matter. That's u and y. So y over u equal to g of s over 1 plus g of s. Okay. Here I have minus, so that's the reason I end up with plus there. If you have plus there, it will be minus. Okay. How do I know that's a plus or minus? It doesn't matter for this example. I just chose negative so that I end up with the positive in the denominator. Anyway, he's asking about find the root locus for this g of s. Don't need to worry about the unity feedback. Now, what is root locus? Basically, what happens? I mean, how the system behaves by varying the k value. That's what we're finding here. So there are several steps. So step 1, locate the poles and zeros of the denominator. The denominator is called characteristic polynomial. When I make it equal to 0, we call that as characteristic polynomial equation. Now, if I make it equal to 0, I end up with s equal to 0. And then the remaining 2 poles. So it's a third order system. So I end up with 3 poles. So s equal to 0 and s equal to minus 2 plus or minus j3 by using the quadratic equation formula. Now step 2, find the loci. I can show you here, but at the same time I'm going to do it on the main graph. I didn't use the main graph in the first video, but I'm going to use the main graph here. So usually I'm going to represent poles with the cross mark. Okay, cross mark is a pole, and 0 with 0. In this given function, I don't have any zeros, so that's the reason we're not going to have any zeros. So I have a pole here, and minus 2 plus j3. So minus 2 plus j3, so that's minus 2, probably I would say plus j3, and minus 2 minus j3. Okay, so those are the 3 poles. I'm going to represent them in the main diagram, but the next point is find the loci. Okay, where we're going to have a loci. Loci is nothing but the line. So again, here is the diagram, graph. So we have a pole there at the origin, okay, and another pole is 2 minus 2 plus j3, minus 2 minus j3. So minus 2 plus j3. Here is another pole. Minus 2 minus j3 is another pole. Now in this step we're going to find the loci. So start walking from here on the on the right hand side towards left. If you see odd number of poles plus zeros, okay, you will have loci. If you have even number of poles and zeros, no loci. Okay, say for example I have a 0 there. Okay, then we'll see how it's going to work. In this example we don't have, but I'm assuming there is a 0. Remember one important thing, root loci is going to start at the pole and at the 0. So starting from here, I see 1 is an odd number, so definitely there is a loci which is going away from the pole, and once we reach here there won't be any loci because I have even number. Okay, so we know that loci is going to start at pole and end at 0. So we have a root locus or loci between those two. Okay, now here that's an even number. So once we pass this even number, once we pass here, that's also even number, so there won't be any loci afterward. But in this given example we don't have this 0. Okay, so let me read minus 1 minus 2. So in this example I don't have 0, all 3 poles. So for sure this loci will continue. Okay, this loci will continue till infinity because it's always odd number of poles plus zeros in this case. Okay, how about the other two? There will be Loki starting from here, but I don't know where it is starting at this point. So once we go over the other steps, we will find where the Loki is going to start. Next step, find the angle of asymptotes and centroid. This asymptote is nothing but, so if you have a graph, Loki is the line, I mean how the system is going to behave by changing the k value. Okay, now this asymptote is nothing but, here is the definition. Asymptote is nothing but, asymptote of a curve is a line such that the distance between a line and curve approaches to 0 as they go towards the infinity. So basically asymptotes tells us which direction the Loki is going. That's what asymptote means. Asymptote is asymptote of a curve. Asymptote is always related to another line. Okay, related to mostly a curve. Asymptote of a curve is a line such that the distance between a line and curve approaches to 0 as they go towards infinity. So here we have three asymptotes. One is going plus or minus 60 degrees, plus or minus 180 degrees, minus plus 60 degrees. And centroid is nothing but at what point they are going through in our graph. That is nothing but minus 4/3. So we'll move to our graph. So here is our graph. So here centroid is minus 4/3, which is 1.33. So this is 1, 1.1, 1.2, 1.33 is going to be somewhere here. This is centroid. The centroid is nothing but minus 4/3. Now you have 60 degrees angle. One is going plus or minus 60, another one is plus or minus 180, another one is minus plus 60 degrees. Okay, so here you have to have proctor to find out the angles, so that way it's going to be easy. So let me show you proctor. I'm sorry, I meant to say protractor, not proctor. So here is a protractor. Okay, so it tells you the angle, so that way you can easily find out where the angles are. So by using protractor, you're going to do these lines. How do I know that 60 degrees if I don't have that? Let me see, can I say this as, say for example this is theta, can I say tan theta equal to opposite over adjacent, right? So I know this distance adjacent, that distance is, so theta is tan 60 degrees. If you don't have protractor, we can find that angle, I mean find that line or draw that line by using this formula. I don't know what is the opposite. Okay, I know adjacent is minus 4/3. Okay, based on this we can find the opposite. So I found that the opposite side length is 2.33, so 2.33 is somewhere here. Okay, and same thing 2.1 to 2.33 somewhere there. Okay, now I have 2 points. Use the scale to draw those asymptotes. Okay, so you have one is plus or minus 60 degrees, so plus 60 degrees, minus 60 degrees, and plus or minus 180 degrees. Another one is plus or minus plus 60 degrees. So minus plus 60 degrees is same as the first one, so I'm going to draw these two lines first. Here I'm using a ruler to draw this line. Usually we'll draw this asymptotes as a dotted line. Okay, passing through that 4/3. Okay, same thing here. I'm not extending in the other side, but it's not going to make any difference if you extend it on the other side, so I'm not worried about that part. So here is the next one. Okay, Actually, it's not going to hurt us to extend on the other side too. Okay, so I will extend on both sides. Now these are the asymptotes, 60 degrees. How about 180 degrees? Basically this is 180 degrees, it's already in there. Okay, so this red line and blue line, so basically this blue line is asymptote, red line is the Loci. They both supposed to meet at 180 degrees, so there will be a small angle between those two, but it's a negligible angle. These two supposed to meet at the infinite distance. Okay, now we need to concentrate how this Loci is going to start from the other two poles. That's what we're trying to find. Next step is finding the breakaway or break-in point. So what is breakaway and break-in point here? So this Loci, the red line, is it going to break away from the real axis at anywhere, at any point? That's what we're finding. In this system, it may not break away, but it's a good idea to find that value anyway. To find the breakaway or break-in points, we need to have a closed loop system. So closed loop system, y by u equal to g of s over 1 plus g of s. So we have k over s times s square plus 4s plus 13 by 1 plus k over s times s square plus 4s plus 13. Okay, so if I simplify this, we'll end up with k over s times s square plus 4s plus 13 plus k. This is the whole system, y by u equal to k over s times s square plus 4s plus 13 plus k. Now take this denominator, make it equal to 0. This is nothing but the characteristic polynomial equation, and make it equal to 0. So we'll take the whole thing, make it equal to 0. So k equal to minus s cube minus 4s square minus 13. This is not b, it's look like b, minus 13. Okay, 13, yes. Okay, I'm multiplying with s. This is the k. Now we're going to differentiate this with respect to s. Dk over ds equal to minus 3s square minus 8s minus 13 equal to 0. Then find the s value. We'll end up with s equal to by using quadratic equation, I end up with minus 1.33 plus or minus j 1.6. Now substitute this s value into k. Now k equal to minus s cube minus 1.33 plus or minus, I mean, since there are two values, we're going to substitute one first and then check with the other one. Minus 1.33 plus j 1.6 whole square minus 4 times minus 1.33 plus j 1.6 whole square, sorry, this is whole cube, whole square minus 13 minus 1.33 plus j 1.6. Okay, plus j 1.6. Okay, now when we substitute this k value, okay, when the s value in the k will end up with it's not a real, it's not equal to a real value. Okay, if it is not real value, then there won't be any breakaway point. Okay, same thing when you substitute k equal to s equal to minus 1.33 minus j 1.6, that is also not equal to a real value. As long as it's not real value, then there is no breakaway point. Okay, as I mentioned, it's not possible here to have a breakaway point because the root Loci always starts at the pole, ends at a 0. I don't have any zeros here, So if you don't have a 0, that Loki is going to go directly towards infinite. Okay, so definitely it's going to go straight in that direction. Next step, step 5 is we have to find angle of departure. Since we have poles here, where this line is going to start, how this line is going to departure from that pole, that's what we're finding here. If you have 0 there, instead of pole, say for example, if you have 0 instead of pole, then we'll find angle of arrival. Okay, there is a small difference in the formula finding angle of departure and angle of arrival. It's almost same, but I'll explain angle of arrival in the next example. So here we're finding angle of departure. So to find angle of departure, say this is pole A. Okay, so what we're going to do, we're going to draw lines from every other pole and 0. Okay, so here I'm going to draw a line from every other pole and 0. So that's one pole, this is another pole. Okay, now find angles from the real axis, every angle from the real axis. So I can clearly see theta 2 equal to 90 degrees. Can we find theta 1 there? Theta 1 equal to, can I say, it's up to you. I know this angle right there is 60. No, we need to find this angle anyway. So can I find this angle x? Angle x equal to tan inverse of opposite, which is 3 over 2. What is that angle there? That value is 33.69. So theta 1 must be 180 minus 33.69. That value equal to, so here theta 1 equal to 146.31, theta 2 equal to 90 degrees. So to find angle of departure, angle of departure at A, equal to 180 minus theta 1 minus theta 2. Okay, this is the formula for angle of departure. Okay, if we have zeros, so probably I might explain that in the next example. Don't worry, to avoid confusion, I'm not explaining that here. Okay, but definitely I will explain that in the next example. 180 minus 146.31 minus 90, that equal, looks like I made a mistake here. Finding the x value, tan inverse of 3 by 2, I have this value as 56.3. okay, this value as 56.3, made a mistake, this is 56.3. so this value here 123.7. okay, so the final value I have A equal to negative 33.7. so this is 123.7 degrees. Okay, so the angle of departure is negative 33.7. I'll tell you how to find that angle here on the Loki. So if you look at on the graph, okay, so here is that's 0 angle. Okay, negative 33, so is going to be some, so you have to use the protractor to find this angle. This will be negative 33.7 degrees. Now at this complex pole, if you have negative 33.7, here at the other complex pole, let me call this as A prime. At A prime, you will have a positive angle of 33.7 here, because remember, one of the root locus is it is going to be symmetry on the x-axis. So basically, once I draw this on this form and fold it along the x-axis, whatever we have on the top, same thing we'll have at the bottom. Okay, the both are going to be, so to have same thing for sure, this must be positive 33.7 degrees. So this is angle of departure. Okay, so this root Loki is going to departure at 33.7 degrees. This is also, that's negative 33.7, this is positive 33.7 degrees. To find the crossing point, take the characteristic polynomial equation of the closed loop system, which I have s cube plus 4s square plus 13s plus k equal to 0. This is for the closed loop system. Where did I find? I believe I found that above here. Okay, so this is the closed loop system transfer function. This is the characteristic polynomial equation of the closed loop or closed system. Okay, now here substitute s equal to j omega. Substitute s equal to j omega. I'll end up with j cube s omega cube plus 4 times j omega square plus 13 times j omega plus k equal to 0. J cube, which is j square, equal to -1. So minus omega cube plus so j square. So j cube is nothing but, I'm sorry, it's minus j. So j cube is nothing but minus j omega cube plus, actually this is going to be minus 4 omega square plus j 13 omega plus k equal to 0. Now here equate the real part equal to 0. We'll make real part equal to 0. So I have real term minus 4 omega square plus k equal to 0. Okay, so k equal to 4 omega square. Here make imaginary part equal to 0. So imaginary part equal to 0, minus omega cube plus 13 omega equal to 0. So omega cube equal to minus 13 omega. So omega square equal to 13. Okay, so if I substitute it here, k equal to 4 times 13, which is 52. So basically this omega value, which is omega equal to square root of 13, which will be plus or minus 3.6. This omega value will give you the crossing point. So 3.6 is, where is it? Right here. 3, 1, 2, 3, 4, 5, 6. So this is minus j 3.6. This is plus j 3.6. Okay, so this line is going to start with the positive angle of 33.7 and it's going to turn. Okay, we need to draw it properly. Yeah, it will be a soft turn but not the sharp turn. Okay, and then it will continue. So basically this blue line, this red line, they're going to meet at infinite. Okay, same thing here. Okay, and then it will continue. So now if you look at this diagram, so don't worry about this here. Okay, now if I fold this paper along the x-axis, now you see you will end up with the same thing above x-axis and below x-axis. Sorry, I took a very long time to make this video and long video. Sorry about that, but I hope this will give you a better knowledge on the root locus. Thank you. I will make couple of more examples. Thanks.